right, let's go ahead and get started. Good morning, everyone. My name's Oliver.
And I'm Pete.
And Pete grew up just close around here. Do you want to tell us any stories from your childhood?
Nothing that I'm willing to put on the record, unfortunately.
Okay, well then, maybe later at Pete's favorite pub. But anyway, we both wound up in Stockholm working for Spotify, and we work in core infrastructure, which is right down at the bottom of Spotify's platform organization. And we're happy to be here. We hope you're all excited to hear lots about Envoy today. And we have plenty of rate limiting use cases at Spotify, but today we're going to talk about rate limiting in our perimeter. We have some history and experience using the global rate limiting in our perimeter, and we had some issues with that, so we wanted to explore a more scalable solution. So what are we going to cover today? We're going to talk about the rate limiting landscape and why we decided to write our own rate limiter. Pete is going to talk in depth about the rate limiter that we wrote. We're going to talk about the different options that you have extending Envoy and how we eventually chose to use Go. And then we're going to talk about our experience actually writing the rate limiter in Go. But before we get to it, Pete's going to give us a little general background on rate limiting.
I'm sure we're all roughly aware of what rate limiting is, but just to make sure we're on the same page. What is it? Well, we want to take some attributes of requests. We're talking about like L7 HTTP requests here. Count the number of requests in a time window, and whenever that limit is exceeded, start rejecting them because it's too many. And the key terminology here that may be unfamiliar to some is this idea of buckets, which is essentially some group of attributes, IP address, path, whatever, and these can be thought of as static, which are generally things that you can know before you deploy your system, URLs, upstream clusters inside your organization, and then there are like dynamic buckets, which may be the IP address requests are coming through via the internet or the user that's making those requests. Just so we're all on the same page there.
Okay, thank you, Pete. So now there's quite a few approaches for rate limiting. Let's take a look at the options that we have. So I'm going to cover 4 options today. We have local rate limiting, we have global rate limiting, there's RLQS, and what you might get from a cloud provider. And shout out at this point to Gemini for our clip art. So first, let's talk about Envoy's local rate limiter. As you might have assumed from the name, it's scoped to a single Envoy. It's super flexible, and it can limit based on a variety of request and Envoy metadata. But it's also useful to note that although it supports dynamic buckets, as Pete talked about, it has a hard limit on the number of values that it can support. I think the default is like 20 or something. So, and this limitation makes it impractical to support common perimeter use cases where you might have dynamic buckets with high cardinality. So all in all, local rate limiting, it works pretty good, but it doesn't support common perimeter use cases like, IP-based rate limiting or user-based rate limiting. So next, let's take a look at Envoy's global rate limiter. So it has distributed state, so buckets are shared between all the envoys that you might have in a group. And it functions in the request path. So that means that on every incoming request, it has to consult an external rate limiter process that decides if the request should pass or be blocked. And this, of course, necessarily adds latency. But let's talk for a minute about scaling the rate limiter architecture itself. So there's the external rate limiter process. There's the reference implementation from the Envoy project. And we also need to have some kind of state storage, like Redis. So at scale, we're talking about lots of rate limiting processes, some kind of clustered in-memory state storage, and needless to say, this is it's a lot of operational complexity. About 5 years ago, I think Tinder gave an EnvoyCon talk that said that the rate limiter pod that they were using, the OSS version, it got about 5,000 RPS. So you can see where this goes if you need to support a few million RPS. So RLQS, the rate limit quota service, we found this pretty interesting. It avoids the latency issues with the global rate limiter, by operating outside of the request path. So there's an RLQS server that issues quotas to your envoys for each configured bucket, and a feedback loop to aggregate the consumption on each envoy and issue new quotas. However, it's very clearly marked as a work in progress and not ready for production use. But still, it's pretty interesting. And lastly, looking at some of the non-envoy options that you might use. Downstream from your perimeter layer, you might have a CDN like Fastly or cloud provider load balancer like GCLB. And these work great if it fits your use case. You know, it's a managed service, you pay for it, but you don't have to operate it. So that's kind of great. However, you can only rate limit on aspects of your traffic which is visible to that layer. So, for instance, if you want to scope your rate limiting to upstream clusters in your Envoy layer, the load balancers can't see that, so it's not useful there. So again, these options, it really depends whether it fits your use case. So now, let's take another look at this list through the lens of Spotify's perimeter use case. So can we use the local rate limiter? Well, we have hundreds of envoys in our perimeter layer, and we want a rate limit on IP or user ID, so no, that's not going to work. The global rate limiter, as I mentioned before, we've run this in the past. We found that operational complexity was just way too high. Scaling the rate limiting infrastructure, it's also a pricey proposition because you're going to have to scale it for higher than your peak traffic, and that alongside the performance of the poor performance of the OSS rate limiter process, it meant that our rate limiting infrastructure could cost more than our Envoy infrastructure, and so it just wasn't worth it for this case. RLQS, as I mentioned, we're pretty interested in some of the aspects of this approach. There are a few technical reasons we can't use it, and Pete's going to go into that in much more depth. But the fact that it was only a work in progress meant that it was a non-starter. And just to touch on the non-Envoy options, I said we want to limit based on user ID. We only decode that in our Envoy layer, so it's not something that we could practically use. And then there were no more options. So where does that leave us? It looks like Pete finally gets to write his rate limiter.
Thank you. So, of course, the most important thing in any project to start with is a name. We chose the name TimeCop. Why did we choose this name? Well, it's very funny to say Jean-Claude Van Damme quite a lot in many contexts. The second most important thing is to have a design. Okay, so what is it that we are actually trying to do, and how can we actually do it? So let's take a step back. What is it that we actually want to achieve with our rate limiter, and why is it we can't get there with the options Oliver has just discussed? So with rate limiting, you have to define some number of requests that are allowed within a given window. And there's a tension here between choosing a limit that is generous enough to avoid affecting normal users and low enough that it defends against unwanted activity. A rate limit of, say, like 10 million requests per second is probably never going to affect a normal user, but it's obviously not going to help you very much. Typically, whenever this limit is exceeded, you could call this like the nth plus one request in the window, you reject that request. This should all be very obvious to everyone. Enforcing such a hard limit for every single bucket, so that's some group of attributes, a user, IPs, services, etc., is expensive and is also somewhat unnecessary. The vast majority of our clients and our users are well behaved the vast majority of our time, and in many cases it's not particularly an issue if a user does stray over a limit accidentally. It would actually be a bad user experience for them. They maybe see an error in the app, or whatever they're doing takes longer because they have to wait for their tokens to refresh and get more access. It also doesn't really help us very much either if we stop 1 or 2 people a day having 5 requests in a second rather than 6 requests in a second, for example. This is the activity that we actually want to stop, way in excess of any reasonable usage, any fair usage, any limit that we could possibly stop. And if we loosen the requirements and the constraints of our system such that we target this kind of activity and we don't try and enforce a particularly hard limit on everyone, everywhere, all the time, we can get greatly improved scaling characteristics of the system. Okay, so what is the scale that we're talking about here? This is a graph of the incoming HTTP requests to Spotify over a week. It peaks at about 10 million requests per second on a typical day. And if certain famous artists release albums, you might imagine who I'm talking about, this can easily exceed that. We have about 675 million monthly active users, 1.5 million Kubernetes pods, and about 3,500 microservices in production. It's quite big, and unless you design for scale, with this scale in mind at the start, you will spend a lot of money on your rate limiting infrastructure, which is kind of waste. So fundamentally, all we have to do is count and aggregate, right? Rate limiting is really a matter of distributed counting and summation. We have hundreds of envoys in our perimeter, and the way it's designed, essentially any envoy can serve any request, even consecutive requests from the same user. There's no affinity, there's no sharding, with some minor exceptions. This means that no particular envoy in the perimeter has enough data on its own, outside of extreme cases, to make rate limiting decisions. So, in the words of Patrick, what we need to do is take all of these counts and push them somewhere else. Now, if you're aware of ROQS, you might be thinking, well, isn't this what ROQS does? And yes, it is. And really, Timecop is ROQS with a fancy hat. So what is it about ROQS that doesn't really work for our use case? So ROQS has two major problems for us and our use case. So firstly, there's this behavior, and I'm quoting the documentation here. The rate limit quota filter, ROQS, requests quota assignments from the ROQS server when the request matches to a bucket for the first time. Due to the nature of our traffic, and because it's horizontally scalable and stateless, nearly every request to one of our envoys will be unique within a short time window, which ultimately means that about one request means that we will have to make one request per request to an ROQS server, which is essentially the same behavior as a global rate limiter, although admittedly that is not in the hot request path. Millions of requests to our perimeter will then be millions of internal requests to the ROQS servers per second. And secondly, there's no sharding of the data from the envoys to the ROQS servers. You end up having to shuffle all the data, the buckets and the counts, between the ROQS servers or to some shared storage like Redis, which is another fairly large set of data moving over the network. Timecop solves these two issues by using consistent hashing of buckets to aggregators and only ever periodically reporting counts, whether or not the buckets are new to the envoy. Instead of having to make essentially one request per request to our perimeter, to our rate limiting system, we now only have to make as many requests per time window as we have aggregator servers. In practice, this is a fraction of the number of requests each envoy would otherwise have to make. Instead of tens of thousands per time window, it's tens per time window. We can now also be sure that the counts for a given bucket are in memory on a particular aggregator. That means we can make local decisions on each aggregator and no longer have to shuffle data around at all. Similar to ROQS, Timecop uses gRPC streams between the filter and the aggregator to receive blocking actions, which is to say, please block this bucket, it's made too many requests. But the astute amongst you may have noticed a problem. If rate limiting decisions are being made locally per aggregator, how do we let all of our envoys know which buckets to block? Each envoy is not connected to every aggregator via a gRPC stream. Well, we use Google Cloud PubSub to distribute the blocking actions between aggregators, which then push them to all the envoys they're actually connected to. Our perimeter system already depends on PubSub, so this isn't a new component we're adding to the system, nor does it affect our SLOs. It does increase the delay in a blocking action to take effect, but usually not by particularly much. And as I've said, we're happy to loosen the requirements of the system, loosen the strictness of the system in order to make it scale, much more efficiently. But again, some of you may have noticed another problem. What happens if we lose one of our aggregators? Well, we don't really care. Most of the data stored in the aggregators is unimportant. Existing blocking actions will still take effect. They've already been distributed to all of the other aggregators, all of the envoys. And any bucket that is teetering on the edge of being blocked will be found and caught by another aggregator when the consistent hashing routes it to another aggregator. Note that you will have a similar problem, though to a lesser degree, if you're using the global rate limiter, as that uses Redis for storage by default. You're unlikely to lose the cluster, but you might. Now, Oliver's going to discuss how we actually built this.
Mm-hmm. Thank you, Pete. So let's take a step back for a minute. So now we have a good understanding of the architecture we want to build, so let's figure out how we're going to build it into Envoy. So we can start by looking at the approaches that we can take to extend Envoy. We'll take a look at C++, we'll take a look at Lua, we'll take a WASM, and we'll take a look at Go as well. And a quick note, we were looking at this list at the beginning of last year, so the landscape has changed a bit since then. And thank you again to Gemini for our logos. So first off, we have the gold standard C++. When you write filters in C++, you get a mature API, full-featured API. Most of Envoy is already built this way, essentially dog-fooding the APIs. But writing C++ filters, it does mean that you have to take on the whole aspect of building your Envoy binary. You may not have been doing that before, and like setting up an entire build process. That's a pretty weighty thing that you have to worry about. So as long as you have C++ expertise and you don't blink at running your own builds, then you can't go wrong with C++. What about Lua? It's simple, it's easy, but what does that mean? By design, it has a fairly narrow API surface, and it doesn't have any support for background processing or custom statistics. So WASM. WASM looks kind of interesting. You can write in various languages. It seems to have fairly wide API coverage. It has a mechanism to do things outside the request cycle. But it's also clearly marked as experimental. The documentation's a bit confusing. I've heard in the past that performance hasn't been so good. Maybe it's better now. I don't know. So let's take a look at Go. You can write filters directly in Go, but at least at the beginning of last year, experimental is quite new. It was in contrib and not in core. And the API, it doesn't support background processing, but we're like, oh, you can spin up Go routines and do things outside of the request cycle. So it has support for native Envoy statistics. And we looked at the code. It looked like a fairly simple implementation, so it's interesting. It's interesting. But before we try and evaluate which option we're actually going to use, let's look again at our requirements. So we need the API surface to support background processing, so we can batch up request counts and send them to the aggregators. Obviously, we need to send requests to the aggregators, and we need support for custom metrics so that we can be good SRE citizens, of course. And from a DevX perspective, we'd really like a language that we already use in our org that allows us to develop quickly. And clearly, for production, we need to make sure it can scale. So, okay, now given our requirements, let's look at this list again. Should we use C++? We know it's going to work, but we're worried about spending too much time using C++ and developing in C++ rather than trying to prove that our rate limiter actually works. And let's face it, C++ is not common in our org. We do have some motivated individuals, however, so we'll give this a maybe. Lua, simple and easy, yes, but for our use case, it's too simple, so it's just not gonna cut it. WASM, in the end, there were just too many red flags. The fact that it was experimental, there were concerns about performance, like seemingly high complexity, documentation's a little weird. Maybe we didn't give it a fair shake, but in our case, WASM, it just wasn't sparking joy for the team. So it gets a big X. Lastly, should we write it in Go? It's experimental, it's in contrib, but it ticks many of our other boxes, especially for initial development velocity. So we'll give this a maybe. So now we're left with two very different options. On one hand, we have C++. It's the de facto choice for our use case, but we're not a C++ shop down in the basement where we develop our infrastructure. On the other hand, we have Go. It's a language that we actively use in our org to extend parts of our infrastructure. Many of our employees use Go and they love it. So by this point, it had kind of become clear to us that we couldn't make one decision that would cover both development and production. So in the end, we chose Go. We chose it for developer experience qualities, which would lead us to an MVP much more quickly. But we made this decision with a couple big asterisks. One, the filter lacked maturity, and it was only in contrib, so we weren't really sure about the level of community support. And we weren't really sure what our development and operational experience would uncover. So I'm going to hand it over to Pete, who's going to tell us how did it actually go.
Sorry for the pun. So the truth is, it started off very badly. Most developers at Spotify develop on MacBooks, and as I'm sure everyone knows, MacBooks have moved to ARM processors in recent years. We do have our own internal builds of Envoy, which we apply some patches to for internal use. But our production servers and our build servers are all x84, 64 machines. And it turns out it's extremely hard to cross-compile the Go, Contrib, ARM builds for OS X on an x84, 64 build pipeline. It's something to do with these CPU flags. Compiler flags. What we ended up doing was just building Envoy locally on our machines, which thankfully is pretty quick on an M1 or MX Mac. This was very frustrating and difficult to work out. Obviously, once you know how, it's very easy, but getting past that was actually quite annoying. So once we had done that, we decided to do some benchmarking of simply the overhead of calling a filter written in Go versus a filter written in C++. Now, I know this graph is not very clear. You'll see there are two lines that are very, very close together. And what this benchmark actually showed was calling a Go filter is faster than calling a C++ filter. Now, clearly, that cannot possibly be true. The benchmark has some limitations, but what it shows really is that the difference is immaterial, right? Out of the box, there is no particular performance hit for calling the Go filter. Obviously, that will change when you put more code into there, and we'll see some better benchmarks later. The first trouble we ran into while writing the actual code was the support for metrics. Metrics are supported, however, tagging them is not supported. So we ended up with some Frankenstein metrics with names like this. Now, thankfully, most of the metrics we want to provide to our customers internally, we can generate from our aggregators, where we have as much metric support as we like. But this was sorely missed, and we would rather not have to make metrics like that. But perhaps the biggest issue was the lack of a sort of direct API to call listeners or clusters in Envoy. So as I said, Timecop is essentially ROQS but uses unary gRPC with maglev. And maglev is supported by Envoy out of the box. So what we wanted to do was just call via Envoy to our aggregators, and all the sharding would happen like that. Unfortunately, since there's no way to do that directly from Go code, what we had to do was expose a Unix domain socket on our pods, have the filter connect via the Unix domain socket, and then pipe it through Envoy. I mean, of course, we could have done that in the Go code, but that really doesn't make any sense when you're inside Envoy itself. So this was another sorely missed feature. So, how did it actually work out once we had built everything? These are two benchmarks of our vanilla Envoy, so our internal build, that does no rate limiting of any kind, no timecop, no other filter, and the same build, but with our timecop filter turned on. And you'll see that we pushed our P50 latency up by 3 milliseconds, and our P99 latency went up by a slightly disappointing 11 milliseconds. Now, while that isn't fantastic, and maybe we can improve that with some further work, further optimization, what it's worth realizing is that when we did run the global rate limiting service, we had a per request timeout of 8 milliseconds. Now, obviously, that was not hit very often. If the rate limit cluster went down, though, it would be hit for every single request. So there were points where, while running that, we were doing plus 8 milliseconds on every single request. So in comparison there, not too shabby. Fundamentally, though, we did ship it. This did go to production for some test services, not test services. It was being tested by some production services, and it did work, and it did block traffic. So this is the end of our story.
This is the end. Thank you, Pete. So thanks, everyone. That's all. We wrote Timecop and Go. We have it in production. Mission accomplished. Although not quite yet. Not quite yet. Not so fast. So we've shown that the whole Timecop system works end to end, but we reconsidered our decision to use Go for the Envoy filter. So we reframed the decision as to what would be acceptable for production, and there were some downsides that we just couldn't ignore. So number one, using the Golang filter introduced an additional language and technology into our data plane, which made us a bit nervous. It turned out that the API surface exposed by the Golang filter, it wasn't quite sufficient for our use case and caused some significant technical debt that we'd prefer not to carry. And the Golang extension wasn't mature to the point of just working. So we decided to double down and rewrite Timecop in C++. And of course, as we expected, porting timecop to C++ wasn't without its own issues. At this point in time, we've almost completely ported the filter from Golang to C++, and the team has experienced a bunch of new language, new skill set problems, like how to set up your IDE, adding support to the build pipeline, debugging, testing, various language issues like coding styles and compiler problems. I think it's fair to say the velocity developing in Go was faster, but we think that the end result in C++ will result in a more sustainable end goal. So, okay, now we're actually at the end of our story. But I want you all to take away two main points. Number one, rate limiting at scale is hard, and none of the available options may work for you. And number two, writing complex Envoy filters is also hard, and you'll have to do it in C++ because no other options are mature enough. And one request to the community, can we please have a stable, mature option for developing filters that's not in C++? And I see one of the lightning talks later might address some of that. So, but with that, thank you all for staying awake to listen to us. And you can see that in our request to write a rate limiter, we wound up in quite a different place than we had expected. And indeed, it was an adventure. So, with that, we're happy to take any questions now, afterwards.
We've got time for one question, I think. And yeah, do we have content for you coming up at 12:15, I think, the new dynamic module stuff? Okay, you're closest.
G'day, nice talk. Could you explain how you're resilient to the aggregator failing? You mentioned the data with PubSub, but how are you resilient in terms of the Envoy connecting to the aggregators?
Yeah, so I mean, the Envoy is obviously just using its standard cluster mechanisms. So the transport is gRPC. The aggregators are registered as a gRPC cluster. They have active health checking. So if a pod gets killed or we're redeploying or something, it does a graceful shutdown, drains, moves on. And again, we're not super worried about the data inside the aggregator. We're happy to lose it. So yeah, it's just standard Envoy cluster management stuff.
Cool. We are up on time. I assume these folks will be around. Yeah, there is a coffee break now. It's outside for 30 minutes. If everybody could be back at 10:40, we've got some folks from Google talking about LLMs.
LLMs.